I'm Clayton Wardwell. I'm a student at Rosa Junior College. And
I am Orlando Raola. I'm a professor of chemistry at Santa Rosa Junior College.
what's your favorite analytical method?
My favorite analytical method, that's difficult to define, Clayton, because there's a group of favorite methods. But I can say that anything that relates to X-rays is my favorite analytical method. And that can be something that you have used, X-ray fluorescence, but can be also X-ray absorption. That is the subject of my research for my master's and my doctoral program. So anything X-rays.
Why do you find X-ray analytical methods so appealing?
Well, X-rays were accidentally discovered. They were not looking for them, and Röntgen runs into this radiation that can go through matter. And the first uses of X-rays were not really analytical; were just imaging. But then other discoveries were made that showed that X-rays can probe directly into the nature of matter, both about the structure of the electrons and also about the way in which different atoms and molecules are spaced in the crystal. And so it's a very large amount of information that can be pulled from the interaction between X-rays and matter. And that's what fascinates me.
So what was the most unusual thing you've analyzed in your career? Not just at your first job, but throughout your time?
The most unusual. I reflecting on that, I can tell you that as a grad student, I had the chance to have a summer research in Japan. I had a host there, a professor in the University of Kyoto, which is like people call the Stanford of Japan. It's a very prestigious university. And we went into several campaigns. And campaigns is the way that they call going to the synchrotron facilities, using X-rays, and doing different experiments. There are two things that come to my mind. The first one is the experiment that I did personally, and the other one that I saw how they did it. And the one that I did personally was the analysis of fly ash, particulate matter, from the trash incinerators in some Japanese city. We kind of knew what it was, but the Japanese government did not allow the release of this data because we found some troubling amounts of lead in the fly ash by X-ray absorption. So it was an interesting time and discovery, and all the red tape that went with it was a very interesting thing. And what I saw they did that I didn't do myself, but I find it fascinating, is the fact that some fish, these are eels, these are fish that they like to eat very much, have inside their inner ear, they have a tiny organ that is a piece of stone. It's called an otolith. It means stone in the ear. So if you section the otolith, you polish it, and you direct the X-rays there, you can see that it's made of several layers. And those layers tell you when the eel was in fresh water or in salt water, because it goes back and forth, comes in, spawns, goes back.
And there's
Somehow like the salmon does here, so their eels do. And by studying the layer structure of the otolith, it's not microscopic, but it's very tiny. They could tell the life history of the eel, and that blew my mind.
kind of like a tree.
Yeah, exactly.
And what might somebody do as an analytical chemist outside of the industrial field?
Outside of the industrial field, well, you can teach it.
Yeah, okay,
You can be
yeah.
a teacher. You can work in the national labs for the government. You can work in healthcare. You can work in the police department. you can work anywhere.
Sounds like there's a job for an analytical chemist
There is.
everywhere.
There's certainly. It will be the last chemist to go jobless.
Really?
Yeah, absolutely.